Okay, welcome. I'll be presenting our recent results into the development of high-performance large-scale graph databases. Graph databases are a class of complex systems that we are using to manage large and complex graph datasets that we usually model with the so-called labeled property graph. In this model, what we have is our graph structure as usual that consists of vertices and edges. But then in the LPG model, we can also use labels and properties, which are really additional rich data that we attach to the graph structure, both to the vertices and to the edges, in order to, for example, provide some categorization of these entities, or to, as in terms of the properties, to attach arbitrary sets of key value pairs to any vertices or to any edges. The major workloads that we have in graph databases are as follows. On one hand, we have the class of online transactional processing, in short OLTP, which are really usually small-scale graph queries, such as inserting vertices or reading edges, or maybe accessing, manipulating with the properties and labels, essentially arbitrary graph CRUD types of accesses. On the other hand, we have online analytical processing, in short OLAP, which are large-scale queries such as running PageRank job, or maybe running graph traversal, or maybe running graph classification with a graph neural network. So let's take a look at where we use graph databases. So they are heavily used across essentially all of the parts of academia, industry, and business, specifically in fields such as social sciences, engineering, biology, and many, many others, even in cybersecurity or medicine. In order to understand the state of challenges that we have in graph databases, we analyzed a lot of different works and code bases of several systems. And then we identified three classes of problems that are still out there and wait to be resolved. So on one hand, we have challenges with the data. So on one hand, the graphs that we have to process are really large, but also rich and complicated, as we saw already, because of the fact that we can have rich sets of labels and properties. And now, in our long discussions with different collaborators, we have the insights that basically they easily have at least 10 times more data that they would be able to process. There is just no such tool that can, at this point, process all the data that they have. So it's very, very hard to deal with these data sets with current systems. The other class of challenges are workload related. So here, workloads that we have are quite hard to scale with current systems, and often are also quite slow. So one example for this is basically what we have, what is published out there. So the largest scale published so far for graph databases is the Microsoft A1 graph database published in 2020, which was scaled to nearly 3,000 cores, which is not really that much when you really want to go for the big amounts of data and compute. And the other class of challenges is that these workloads are usually very diverse. And then the problem is that the vast majority of systems focus on either one of these workload classes or the other, but not both. And final class of challenges are system design related. So here, the point is that these systems are just very, very complicated. And it's quite understandable because we have to deal with all these aspects of the data and the workloads in terms of running them as transactions with certain properties like ACID, dealing with complex sharding replication schemes, with indexing structures, handling of errors, and many, many others. All of this in the context of distributed memory systems, if we really want to go for the big scale. So a very concrete example for this complexity of the systems is as follows. In one of the repositories of the system that we are analyzing, one of the top systems that we are analyzing, there was literally a comment in the code that said, look, this OLAP query that is basically implemented here, we don't really know what are the effects of running this OLAP query in parallel with OLTP queries, so you'd better not do it in your production code. Right? So that really shows that these systems are hard to design, maintain, and extend, and also hard to port across different architectures. So let's again take a look at all of these challenges. We have 6 of them listed on the left side, and now we would like to have a system that really targets all of them. So we'd like to have a graph database that is programmable, that can be easily ported across different architectures, that is able to support all the major classes of workloads, that also comes with high performance, high scalability, and is able to support really big graphs. Right? So how to achieve all of these objectives in a single design? Well, for this, we developed something that we call the graph database interface, which is really a paradigm for developing such systems that ensure all of these objectives simultaneously. The driving observation in the GDI design was the fact that we don't really want to build such a complex system directly on top of the hardware, right? So if we have our hardware access layer, and if we want to build a database right on top of that, this would easily lead to the design being hard to maintain code and giving us a lot of headaches. So that's really what we don't want to do. But then we realized that basically a certain thing was quite similar in the HPC field. So the key idea here was our observation, based on the observation that MPI was dealing with something very similar a long time ago, right? And the idea here in GDI was to bring the best practices of MPI and its fundamental design feature into the landscape of graph databases. And this feature is basically to break down the complexity of the design of graph databases with the separation between the interface, the API for the design, which is hardware agnostic, and the underlying hardware specific implementation for a given class of systems. So what we have in MPI is the separation between the hardware agnostic MPI standard, which is the API, which is really a fundamental, just a kind of a toolbox with building blocks for communication in a parallel setting, and enables a portable and productive API, being hardware agnostic, and the underlying MPI implementation, which is specific for a given architecture. So that means that it's much easier to build an HPC application if we can use this hardware agnostic MPI standard API for building it. It enables portability just by its design. This is what we do this is exactly what we decide to do in GDI. So we have also now we propose the GDI standard, which is really the API coming with a fundamental performance critical building blocks that we can use to manipulate with the graph data layout and with running graph transactions in a parallel setting. And it enables a portable and productive API for building large-scale graph databases. And again, as it's hardware agnostic, it means that on one hand, it makes it easier to build graph databases that are going to be portable. So really this feature, this design decision by default makes these systems portable, facilitates portability. Now, but it also helps a lot with two other of these challenges, namely making them programmable and versatile to different classes of workloads. So now let's take a look at how we deal with these two other challenges. So now we are going to again focus on the GDI standard, the first part of the whole GDI effort. And you can think of GDI standard basically as a set of building blocks that we can use to construct graph databases easier, portably, and help us build systems that are just hard to navigate and don't give us headache. And as we really care about performance in the end, the main focus on in terms of the construction of these building blocks was the data and the operations on this graph data. That means that we have classes of routines defined in the GDI standard for dealing with graph data, with graph transactions, with the indexes for the graph data, and several others. Now let's take a look at one of the design ideas that we have in the GDI standard, namely formulating OLAP graph queries as graph collective transactions. So we have, as a set of routines, we have routines for manipulating graph data with its vertices and edges. Then we have also graph transactions that are used to manipulate with this data. And these transactions are spanning the scope of these graph transactions spans both the OLTP and the OLAP queries. And now one of the ideas we have in GDI standard is to formulate large-scale OLAP queries as graph collective transactions. And the name collective has is directly borrowed here from the MPI. So this is one of our design ideas to make the semantics of these graph collective queries basically as well defined as we have in the MPI. So for example, when we have, let's say we have some graph database user running some graph queries And for example, if they want to run a large-scale OLAP job, such as triangle counting, they would be using the collective transactions for that. So assuming that we have the blocking semantics, each process that participates in that OLAP query must have finished its participation in this call before exiting this routine, the closing routine. Right. Then, of course, we have also the OLTP queries, so that we refer to as the local queries. So these are the queries that that can be started by a single process. They may affect the memories or the state of other processes, but they are started by a single one, and they can be run completely independently of each other. So then the user A can issue some local transaction with queries like updating vertex property, or maybe inserting new vertices, or doing something else. Then closing the transaction to commit it. But then again, if the user wants to run a collective call, such as BFS traversal, in that case, that means that all of the other users also have to run it. But then if we have the non-blocking semantics, then we can just exit without the synchronization, and the process can poll for completion afterwards. So that sounds like a very simple idea, but it's actually quite powerful, because it really does improve programmability of these systems. Namely, the semantics of running parallel OLTP and OLAP are now well defined. And this comment that we saw before, that okay, we don't really know what is going to happen if you run these things, if you run these two types of queries, OLAP and OLTP concurrently, this will be now fixed with that approach that we are taking in GDI, or at least reduced in its complexity to be resolved. So we have a full manuscript that contains all the routines included in the current release of the GDI standard. You can take a look at this online. And again, we really build it basing on the best MPI practices. So the structure and the contents are similar in style, because again, we tried in this project to harness the best practices that we had in HPC for the domain of graph databases. So this is how the GDI standard handles both the programmability and the versatility challenges in graph databases. Now let's take a look at the second class of our challenges, the performance-related challenges and the scale-related challenges, and how the GDI implementation now addresses them. So GDI implementation can be the implementation for a selected class of systems, and we selected RDMA systems. So one of the key mechanisms, because we use more of them, but one of the key mechanisms we use for achieving high performance is one-sided non-blocking RDMA. So let's have a very quick refresher on what RDMA is. So if we have several processes sitting on different nodes of a machine, such as the one we can see here, they can using RDMA one-sided calls, they can access each other memories with routines such as puts or gets that transfer the data to or from the remote memory without even realizing the remote side that there is some ongoing access, right? As we use non-blocking accesses, we also need to issue separate flushes to ensure the consistency of these accesses, of these memories after the accesses. And we like RDMA one-sided because it comes with certain advantages for performance, namely, for example, no overheads from interrupts at the remote site or no operating system overheads. But now there is a question of, okay, we have these very rich and complex irregular graph data sets with labels and properties, and how do we manage them, manipulate them in the RDMA setting that doesn't really come with a lot of native support for such complex and rich data sets? For this, we propose the GDI-RMA data layout that consists of two parts. On one hand, we have the underlying part called blocked graph data layout, which really is a memory pool, a distributed sharded memory pool of fixed size blocks that serve as our storage for keeping this graph data, right? And the blocks are fixed in size, which means that the design facilitates efficient RDMA operations and simplifies memory management. However, it would be very hard to deal with this, with such a blocked graph data layout when actually coding these graph transactions. So to make it also easier to program these workloads, we'll also provide the so-called logical layout that sits on top of the blocked graph data layout. And the logical layout provides support for flexible size data structures. For example, like the one we can see here, the vertex holder object, which is really a contiguous object that is physically mapped to a set of blocks that can be distributed all over the machine. right? And the size of this logical layout is flexible, which means it's easier to program this. That's really what is visible during the transaction implementation. If you want to implement a transaction, that's what's going to be visible. Now this vertex holder object contains a couple of fields, such as the header with some control information, the addresses of all the blocks that are forming this vertex holder, and the actual label and property data. And then we have more of these fields, but you can check all of them in the paper. Now, there are certain design decisions, again, that are tuned for high performance. So on one hand, if a vertex can fit into a single block, then the best case for fetching the vertex data to our local store for running transaction is going to take just a single RDMA get, which is going to be quite fast. And of course, block sizes are fixed, but also configurable. So depending on your knowledge of your data, if you know that the bigger block size might benefit or the smaller block size might be more beneficial for you, then you can just go ahead and change the block size to be something that you see as the right one. So now let's take a look at how this works in practice by looking at an example graph transaction. Let's take a look at something simple, namely a single vertex update, in which we are going to insert a new property into a vertex. At the GDI development level, this would look very simple. So in the simplest, there are different ways how you could implement this, but the simplest one would be basically 3 calls, namely GDI start local transaction, then the call to add this property to the vertex, and then the one to commit the transaction. So what happens underneath is that first we create some local data structures, and for this we query an index to find and fetch the first primary block of our vertex holder object, and at the same time acquire a read log, because we are now going to read the object first, so we need a read log. Then we fetch the actual block data and create the local logical representation. So we have now locally the header and the addresses of all the blocks. So this is what is contained in the primary block. And then we use these addresses of the blocks to fetch all of the other blocks that form this vertex from anywhere in the system. We use RDMA get calls in parallel for this. And then we actually want to do the modification to the vertex data. So at this point, we need to set the write log, and after that, we can add this new property locally. After that, we want to commit this into the global state to finalize the transaction. So we do it with concurrent RDMA puts, and we finalize with releasing the log and releasing the local data structures. So there are some of the decisions we took here in our RDMA design, again, to maximize performance. Is, for example, fine-grained reader-writer synchronization and parallel updates with non-blocking RDMA puts and gets. Now we have hundreds of similar protocols for different types of graph CRUD manipulations and accesses for different OLAP queries, and you can check all of these things in our online repository. And finally, what we also did here was to provide theoretical performance guarantees for nearly all of these protocols in terms of their work depth and communicated data volume, in order to achieve also performance portability or facilitate performance portability. In our evaluation, thanks to the generous support from the Swiss Supercomputing National Center, we are able to use the full scale of the PSDANE supercomputer that amounts to more than 120,000 cores and more than 7,000 servers. So let's take a look at some OLTP evaluation. On this plot, we can see this is a histogram, and on the x-axis we can see the latency to run an OLTP query. So here we are focusing on vertex updates. On the y-axis, you can see the number of queries. So we run a lot of such queries, and then we plot all of them to get some statistical information. On the y-axis, you can see the count of such queries that achieve a given latency. And different colors of these bars correspond to different scales. So we have the data for 1 node, 2 nodes, 4 nodes, and 8 compute nodes. And we compare this now to 2 other graph databases, namely to the Janus graph, which is an actively developed graph database built by, among others, IBM, Google, and some others, and also to Neo4j, which is really the #1 most popular graph database used according to the DB Engines ranking. And of course, each system runs fully in memory. And now one observation is that we do have very low, even sub-microsecond latencies for for some of these queries, while we have some outliers, we don't really have that many of them. Well, compared to the competition, because we can see that on one hand, they have much more outliers, and also the speedups that we have are quite significant, right? So we have speedups of around 1,000 over Janusz graph, and then around 3,000 for Neo4j. I mean, there are some queries that are faster for Janusz graph, but there are not that many of them. And the reasons for these performance improvements are really the fact that we focus on harnessing the advantages of RDMA one-sided non-blocking for our design. Now let's take a look at some larger scales for OLTP. So on this plot on the x-axis, we are plotting number of servers from 8 up to more than 7,000. This is also simultaneously increasing the graph size. So this is the weak scaling scenario. On the y-axis, you can see the throughput of a database in millions of queries per second. And different data series correspond to different types of workloads. So we tried different compositions of read and write accesses. So on that plot, we can see both the data for 99% of reads versus 1% of write, which is a very commonly used scenario in different realistic benchmarks. We also tried different compositions of 80% reads versus 20% writes, and even others that you can find in the paper. And then we also run these. So Pisdaint, our test bed consists of different types of nodes. It has XC40 and XC50 nodes, and we use them both. And then for the biggest run that you can see on the right, we used both types of nodes at the same time to achieve maximum scale. And this plot does show that our design successfully scales to more than 120,000 cores, which is really the largest run ever in terms of OLTP workloads in the graph database literature, increasing the hardware scale of cores by more than 40x versus the Microsoft A1 graph database, and by around 950x versus what was published before for Neo4j. We don't plot other systems here because they had around 10x smaller throughput consistently, or even smaller. Let's also take a look at some OLAP queries. Here we are running a BFS traversal. Again, we scale from one server up to more than 7,000 together with the graph size. Here we compare on the y-axis, you can see the runtime of a BFS query. And here we compare the GDI design, which is our shortcut for GDI-RMA implementation, to the Graph 500, which is a tuned implementation of the BFS used for benchmarking high-performance systems. So on one hand, we can see again that we scale successfully to the full size of Pisdaint, which is on the other hand, this time the largest run ever for the OLAP queries in the literature, improving by more than 26x versus larger scale published for the Tiger graph database, and 950x versus Neo4j. And this is, we can see something very interesting here. So we are expecting to be slower than Graph 500, and we indeed were slower for nearly all of the data points, because again, Graph 500 is a tuned BFS implementation which doesn't really support any other workloads rather than BFS, and it doesn't do graph updates or transactions. And we're slower by around 5x to 3x for most of these data points. But for the biggest, for the scale of 2,000 nodes, we are actually slightly faster, which was very, very interesting to see. So the second class of challenges are now resolved by the GDI implementation that you can find online. And with this slide, I would like to conclude. So in our effort, we devised the graph database interface, in short GDI, which you can really think of as the MPI for graph databases, because it enables principled design implementation of these systems, and it consists of two parts. On one hand, it comes with the GDI standard that facilitates programmability, portability, and versatility to different workload classes. On the other hand, it comes with the GDI implementation for RDMA systems that facilitates high performance, high scale, and support for big graph datasets. Thank you for your attention.